Hello students, welcome back to geometry. Today we're going to be talking about the side-side-side congruence theorem. So what the side-side-side congruence theorem says is that, similar to the side-angle-side congruence theorem, if we can show that certain parts of two triangles are congruent, then we can prove that the triangles themselves are congruent. So for example, let me draw a triangle here. And actually, let me draw a nicer triangle. And then I'm going to use my technology here just to copy and paste it so I have truly congruent triangles. There we go. And let me label them A, B, C, and D, E, F. So what the side-side-side congruence theorem says is that I can show that this set of corresponding sides is congruent, and this set of corresponding sides is congruent, and this set of corresponding sides is congruent, then the triangles themselves must be congruent. So I will say, if all three sets of corresponding sides are congruent, then the triangles must be congruent. Let's see how that looks in a proof. So, given KL is congruent to NL and KM is congruent to NM, prove that KLM is congruent to NLM. So, step one, we'll start off easy. Segment KL is congruent to segment NL. That means this is congruent to this, and so now I have one set of corresponding sides. The reason for that is it is given. Step two, I can say KM is congruent to NM. And again, the reason is given. And now I've shown that another set of corresponding sides is congruent. So the last thing is I need to show that one more set of corresponding sides is congruent, and that would be this side right here, LM. And since LM is the same on both triangles, I can say that LM is congruent to itself, LM. And the reason for that is the reflexive property. And that gives me the third set of corresponding sides. So now, since all three sets of corresponding sides are congruent, I can say step 4, triangle KLM is congruent to triangle NLM. And that is because of the side-side-side congruence theorem. Now, the other theorem that we're going to talk about is the HL congruence theorem, and the HL there stands for hypotenuse leg. I'm going to take a short side trip here. So this is having to do with right triangles. And if you remember from earlier math, right triangles have a 90 degree in there, and we have the Pythagorean theorem that goes along with right triangles that says a squared plus b squared is equal to c squared, where a and b are the legs of the right triangle and c is the hypotenuse. Well, the way that works is, let's say this side is 3 and this side is 4. If I wanted to figure out what the hypotenuse is, I would say 3 squared plus 4 squared is equal to c squared. So that would be 9 plus 16 equals c squared. 25 equals c squared. So that means that c is 5. And that is true for all right triangles. Now, that's not what we're going to be doing here, so I'm just going to erase that. Just quick refresher. But by using the Pythagorean theorem, let's say that I have two right triangles. So if I have this right triangle and this is 3 and this is 5, and this is 3 and this is 5. Well, using the Pythagorean theorem, on both of these, I could say that the third side must be 4. So therefore, these two triangles are congruent by side, side, side. So if I can get to the point where I know that it's a right triangle, the hypotenuses are congruent, and one of the corresponding leg sets is congruent, then side, side, side is implied, so these two triangles must be congruent. So the hypotenuse leg congruence theorem is if two right triangles, and again I want to emphasize that they have to be right triangles in order for this theorem to work. If two right triangles have congruent hypotenuses and a set of congruent corresponding legs, then those triangles are congruent. Okay, let's see how that works in a proof. So in this proof, given that WY is congruent to XZ, WZ is perpendicular to ZY, and XY is perpendicular to ZY, prove that triangle WYZ is congruent to triangle XZY. Now in cases like this, I really like to draw the triangles separately because right now they're overlapping, and I would like it better if I could see them. So right here I have WZY, and right here XZY. So the first thing I want to look at is these two perpendicular lines. So that means that this angle is a 90-degree angle and this angle is a 90-degree angle. So since they're perpendicular, I can say step 1, WZ is perpendicular to ZY, and that is given. And from there I can say step 2, triangle WYZ is a right triangle. And the reason for that, I would just put that is the definition of perpendicular. Perpendicular means it's a 90-degree angle, and if there's a 90-degree angle, then that means it must be a right triangle. Okay, step 3 is going to be the same step, but for our blue triangle over here. I would say XY is perpendicular to ZY, and that is given. And that means that triangle XZY is a right triangle. And that is because of the definition of perpendicular. So now that I see that I have right triangles, I'm allowed to use the HL congruence theorem. So step 5, I've got WY is congruent to XZ, and that was given. So I've got this side right here is congruent to this side, and remembering that the hypotenuse is always directly across from the 90-degree angle, I've just shown that the two hypotenuses are congruent. So since I have the hypotenuse now, all I need to show is that two of the legs are congruent. So if I'm looking at that, that means I either need to show that WZ is congruent to XY, or that ZY is congruent to ZY. And oh, if you look at that, I just said ZY is congruent to ZY. And if you look at our picture up here, you see that it's the same segment but on both triangles. So I can actually say step 6, segment ZY is congruent to segment ZY, and that is because of the reflexive property. And now after that, I can say step 7, triangle WYZ is congruent to triangle XZY. And that is because of the HL congruence theorem.